Hypersurfaces are generalizations of the two-dimensional planes in three-dimensional space that you have probably studied. And they are generalizations in different senses. First of all, the space in which they live, instead of being three-dimensional, can be d-dimensional. They themselves are higher dimensional too. They will be d-1 dimensional. Sometimes this is expressed as having a codimension 1 because they have one dimension less than the space-time or space in which they live. And third, the space-time in which they live can be curved, and they themselves can be curved as well. So the definition can be stated as follows: is you have a differentiable manifold of dimension d, and then a sub-differentiable manifold, which we will not define in a very rigorous way, but clearly it has to be itself a differentiable manifold, which is included in MD and has dimension d-1 or codimension 1, is a hypersurface. How do we define these hypersurfaces? Well, typically they are defined by a single function and an equation of these forms of a single function of the coordinates of this MD. This is expressed certainly in some given patch, coordinate patch, and the equation is just expressed like this. Okay, for instance, we can think in Minkowski spacetime or in any other spacetime of hypersurfaces given by constant values of the time. Okay, if I want to express it in this way, I would write t minus c equals 0. Clearly, these spaces are three-dimensional because time is fixed, but I can still move in the other 3 dimensions, proving that this is actually a differentiable manifold. Maybe a bit more complicated, and that it is really a hypersurface. Okay, you need to know all the technical requirements, but intuitively this clearly meets the criteria and the intuitive idea that we have of what hypersurface is. We can think of many other expressions like this. In general, it is convenient to study not just a single hypersurface like this, but the families of hypersurfaces given by constant, where all this constant takes any possible values. Okay, if we think about this, okay, this could be, instead of t equals 0, this could be the same as this, the generalization, a family of hypersurfaces. And again, if certain conditions are met, you can think of these hypersurfaces, okay, at a given time, then evolving. Okay, this will be t equal 1, and so on. And you could think that this family of hypersurfaces fills the whole space-time. In this case, you are talking about a foliation of the space-time. Okay, you can do this not only with time, but with other coordinates. But you see that this is clearly an important and particular case. One way of dealing with these hypersurfaces would be to define some coordinate that I can call, for instance, psi, and which I define as f of x. Then I can use this function to solve one of the coordinates in terms of the rest of the coordinates and psi. Here it is just trivial. You don't want to replace t by psi, because it would be another way of calling t up to some shift, some constant shift. But suppose, for instance, that you are considering spheres is in Minkowski spacetime. So you have this function x squared plus y squared plus c squared. And a good definition, I mean, this coordinate, instead of calling it psi, I would call it r. then clearly I can replace any of these coordinates by r and the rest. So I could have, for instance, x could be r squared minus y squared minus c squared, and then I can replace x by this coordinate r, y, and z everywhere. Then in a second step, I can fix the value of r. Okay, we will do this in more detail later. Okay, what is interesting about this general expression of the equation of hypersurfaces is that it helps you to find vectors which are normal to these hypersurfaces. Okay, these vectors normal to these hypersurfaces are clearly vectors which are tangent to the r equal constant, to the r axis, so where r changes value. Okay, so we can write, we have spheres. Okay, they give some relation of the space-time. Okay, they should be concentric, but don't take. Okay, so at any point you have these are r equal constant surfaces, and this is the r axis at different points. Okay, this tells you how r increases for fixed values of the rest of the coordinates, and the tangent to these lines is clearly like this. This would be some radial outward pointing vector, because it points to the direction of rho in r. And as you can see, this is tangent to this axis, but it is orthogonal to these hypersurfaces. So this vector v will be normal to them. And how do we find them? Okay, tangent to this axis r means that basically we can okay, this is written as a one form, but you can raise the index if you have the need. Okay, that you just have to take this derivative to find vectors which are tangent to r, okay, which is just f, and which are normal to these hypersurfaces. Okay, and of course you have to evaluate this at the value of f or r equal to the constant that controls this, that defines each of these surfaces. Okay, if you want vector which is normal to this one here, you have to fix the value to the constant, I don't know, 1 or 2 and so on. Okay, here it looks like it will always be the same here and here. Okay, if you fix the angle, but you can think of other surfaces that grow in a that foliate the space-time in a more sophisticated way. Okay, so this would be the vector, in this case described in a covariant way, normal to this family of hypersurfaces. Actually, this gives you a complete vector field, which is normal to these hypersurfaces at any point. If you, if they fill the whole space-time, clearly you have one vector at each point, because at each point there is one of these hypersurfaces, and one vector which is normal to them. So these vectors also are defined at every point in space-time. It means that it is a vector field. Okay. So in the case that we have considered at the beginning, which is time equal constant hypersurfaces, well, you would think that it is appropriate to call these hypersurfaces space-like, because all the vectors tangent to these hypersurfaces are space-like vectors. Okay, time doesn't change for them. They are directed in the directions tangent to the space coordinates. So it's intuitively you expect this to be space-like. And indeed, you can classify all the possible hypersurfaces by the properties, the causal character of this normal vector. So you would call this hypersurface time-like if the vector is space-like. v square is smaller than 0 in my conventions. The hypersurface will be space-like if v mu is time-like, which is the case that we had considered. Okay, clearly, if f is t minus a constant, the only component will be the time component, and clearly you are going to have v squared larger than 0. So it's the case that we considered before is falls clearly in this definition. But you can also have null hypersurfaces, and this happens if v mu is null. Okay, and this is maybe unexpected. Okay, if we have a differentiable manifold with a metric, if MD, the larger space-time, has a metric, it's a Riemannian space or pseudo-Riemannian space, then there is a way in which these hypersurfaces, these subspaces, inherit a metric, and this metric is called the induced metric. Okay, there is the best way to find this induced metric is to define this new coordinate in terms of the function that defines the family of hypersurfaces. Replace one of the coordinates by psi, and then you use also the other two if you are in 4 dimensions, and then fix the value psi equal to whatever constant, and then you are going to find automatically a lower rank metric, which is the induced metric. So, for instance, the simplest case, if you have Minkowski spacetime, then dt squared minus dx squared. Okay, so suppose that I have hypersurfaces of this form, which are space-like because my vector is going to be delta mu t. This is the only component. The time component will be the only one which is different from 0, and the value is 1. So I don't need to do anything because the metric is already written in terms of this coordinate psi, because psi is t. Then when I fix t to any constant value c, what I get is ds squared equal to minus dx squared, which is a 3-dimensional, well, the metric of a 3-dimensional space, and it is the induced metric on the constant time hypersurfaces, sometimes called constant time slices of the space-time. That's another word that is sometimes used. Okay, this is very simple, but you can think on more complicated situations, and we'll consider more examples later. If I have some x equal constant, then I get the same, but clearly the metric that I get will have a signature 1, 2, or plus, minus, minus. Okay, and I have another Lorentzian metric because I have Lorentzian subspaces, okay, which are characterized by a constant value of the coordinate x. These are, if you want, the simplest cases. The surprise, because here, well, it is a rank 3 metric. In the case you have 3 by 3, you can write this as a 3 by 3 matrix, which is not singular, and this coincides with the fact that you have a 3-dimensional space. Here, this is also a rank 3 metric. It is a 3 by 3 matrix. The signature is plus, minus, minus because it is Lorentzian, but still it coincides with the dimension of the space-time. What is not so evident is that if I have a null hypersurface, and a null hypersurface could be, for instance, u equals 0. Okay, remember that for x plus. Let me write x plus because maybe it's less ambiguous. So these coordinates x plus minus are defined as 1 over square root of 2 t plus minus x. Okay, this is the definition. And remember that in these coordinates, the metric takes the form, the metric of the Minkowski spacetime takes this form. Okay, well, I have already written the metric using psi, okay, which could be this x plus equals 0 or x plus equal constant. Okay, but this would be psi. So if I fix x plus to some constant value, dx plus is 0, and what I get is a rank 2 metric. So in the null case, the metric is singular, if you want. It's singular if you think that you have still a three-dimensional subspace, because this is just a single condition. You only eliminate one coordinate, and your space is described by x minus, y, and z. But the metric, the induced metric, is only rank 2. So you can think that it is a 3 by 3 metric with a 0 here and minus 1, minus 1. It is singular, or people prefer to think on a metric which is non-singular, but which is valid only for sections with x minus equal constant of this metric. Okay, maybe what I have said just now is a bit complicated for you to visualize. So just think on this, on the fact that null hypersurfaces, the induced metric on null hypersurfaces is always rank 1 dimension less than you might expect. This description of the induced metric that I have just given you has the problem that it is coordinate dependent, in the sense that, okay, I am making explicit use of one coordinate defined as the coordinate that is equal to the function that defines this hypersurface. There is a better way, better in the sense that it gives you a description which is coordinate independent. And first of all, one needs to define the vector, the unit vector normal to the hypersurface. And mu, and the way to construct it is to take the vector which is normal, and we have just defined, and divided by the absolute value of v squared. Okay, this means that n squared can be plus 1 if n is time-like, and the hypersurface is space-like, or minus 1 if it is space-like. Okay, the case in which it is null cannot be handled in this way, and I will describe it later. So for time-like and space-like hypersurfaces, I define the unit vector in this way, and then I define the induced metric in this form. So it is d mu nu minus or plus n mu n mu. Okay, let's see that this definition satisfies the properties that we expect from this induced metric. So first of all, one thing that we expect from the induced metric, well, it is a tensor, okay. It's a symmetric. The rank, we can show that it is just 3, and we can show it in this way because we just need to show that it has null eigenvectors. So if you contract h mu nu with this normal vector, okay, this gives you n mu because you just lower the index minus plus n mu and n squared. Okay, so for n squared equal plus or minus, which is what corresponds to these two signs, this gives you identically 0. If n is a null eigenvector, so this doesn't mean that it is a null vector. Okay, the causal character is still the same. It is either time-like or space-like, but this is in principle, this is a 4x4 matrix, and you can ask the question of what are the null eigenvectors of this matrix. In this case, n is one of them. But you can check that for any other vector which is normal to n, this is not going to happen. Okay, this means that it has one null eigenvector and three vectors which are non-null. And if you diagonalize it, you diagonalize h mu nu using n and another three vectors, you can put it in this way, depending on the causal character of n. So for a time-like hypersurface, the metric can be diagonalized in this way. Okay, this is a time-like hypersurface, and this would be the place of the space-like normal vector. And for a space-like hypersurface, you can diagonalize it in this way. So this is space-like. Okay, after you diagonalize it. Otherwise, well, you don't need to fix coordinates, and you can deal with this h mu nu with this general expression and work with it, and there are many results that you can obtain just by using this general form of the metric. So what happens in the so this was for time-like, for time-like, time or space-like. What can we do in the null case? The normal vector v mu is null, so it doesn't make sense to normalize it. And what you do is to introduce another null vector, an auxiliary null vector, which is normalized with v in this form, so it satisfies this property. Is equal to 1. Then the induced metric is defined in this way: minus L mu n nu minus v mu minus v mu L mu, or in this way minus 2 L mu v mu symmetrized. Well, now you can check that L mu h mu nu is equal to 0, and v mu h mu nu is equal to 0, and then there are two null eigenvectors, and h mu nu has only rank 2, as we knew that it would happen by general arguments. Okay, as rank 2, if we were in d dimensions, it would have rank d minus 2. Okay, so far we have seen how we can associate to a family of hypersurfaces unit vector, okay, a normal vector in general. And then there is the question of when there is the reverse is true. So if I am given some vector, covariant vector or a one form, n, okay, defined in this way, when there is a family of hypersurfaces fx equal to c, to which this n is orthogonal, and by orthogonal we mean that n mu is proportional to the mu of f, because we know that if there is this family of hypersurfaces, the vector normal to it will be these partial derivatives, and proportional to it means that in general there might be some function g of x which is the locally a proportionality constant, okay? Or if you want to write this in terms of differential forms, you would say that n is equal to g df. This is the question. When is there such an f and such a g? Okay, the necessary condition, okay, it is in fact necessary and sufficient, is that this f exists if n satisfies this property. Okay, this property is called, because it means that there is such an f which characterizes a family of hypersurfaces to which n is normal. This is called hypersurface orthogonality condition. And the theorem that tells you that this condition is really necessary and sufficient for this f and g to exist is called the Frobenius theorem. And this particular Frobenius theorem is just a particular case of a more general Frobenius theorem that you can study in one appendix of Wald's book on General Relativity. The proof of this theorem is very simple, but it makes use of differential forms and of the exterior derivative that we decided will be explained in the advanced course, so I will not give it to you. Now what I am going to do is to review a few examples, although we have already seen very simple ones. And the first of them will be that of a hyperplane in Minkowski spacetime. A hyperplane is just a particular case of hypersurface, which is flat, of course. And the formula that characterizes this kind of hypersurface is can be written like this. Okay, where this is a set of constants. If you think on this a mu as a sort of vector, which in Minkowski is still okay, this expresses that the vector a mu and the vector x mu are orthogonal. Or you could write this as this. And then this function, what it does is to restrict the values of x to, if you take a point, so 0 for instance. So let me draw this a bit better. So you have the point 0, okay, the origin belongs to this hyperplane, and this would be x mu here, and all the vectors x mu that belong to this hyperplane are orthonormal to a mu, so vice versa, a mu is orthogonal to these vectors x mu and by extension to the whole hyperplane. It is trivial to find the normal vector using the general formula, but then you find that this is nothing but a mu as you expected. Okay, then there are different possibilities. The causality of this normal vector is the causality class of this vector a mu, and depending on this causal character we can do different things. So if a squared is larger than 1, so a is time-like, it is always possible to perform a Lorentz transformation such that okay, a mu is transformed into the components are transformed into a prime mu, and that the only component that is different from 0 is a0, okay, and the rest are 0. So we can write something like this. Okay, this expresses this condition. So for mu equal to 1, 2, and 3, you get 0, and for mu equals 0, you get delta 0, 0 is 1, and then you get a0. And certainly a0 within x up or down is the same in my conventions. In this case, the equation for these hyperplanes in these modified coordinates takes this form. Okay, now these are primed, is equal to 0, and okay, the solution is that x prime 0 is 0. So these are constant time hypersurfaces, and because they are constant time hypersurfaces, they are space-like. So this is time, and the vector normal vector is time-like, and the hypersurfaces are space-like. Okay, if you want to normalize v mu, well, you only need to take in this new coordinates a prime 0 equal to 1. So let me call in the normal coordinates, you divide by a squared and so on, and what you get is that in this prime coordinates this is just delta mu 0, and the induced metric takes this form, and then observe that this only modifies the 0, 0 component, because otherwise this term wouldn't be different from 0. And when mu and mu is equal to 0, this the value of this is 1, so you have eta 0, 0, which is 1, minus 1 is equal to 0, and the rest of the components of h mu are exactly those of eta mu. So if I write this as a matrix, this is clearly 0, minus 1, minus 1, minus 1. And this is basically what I told you before. Okay, there could be other possibilities. So a squared might be 0. In that case, I can always perform a Lorentz transformation such that n mu, which is already normalized, okay, has this form. Okay, this is equivalent to the coordinate. This gives you x plus equal to 0. In this, sorry, I need a prime here. And I can find an n mu in these coordinates, which would be 1/2 and 1/2. Sorry, if I write the index up, my convention is that this should be written in this way. Okay, they are not the same, because this means that if I write this as a row vector, I have to lower the indices, and this would be 1 over square root of 2 minus 1 over square root of 2, 0, 0. Okay. Okay, if I do this in terms of the coordinates x plus and x minus, I get what I explained before. So let me find the, or let me study the induced metric in terms of these vectors n and l. So, sorry, by definition, we said that this is eta mu nu minus L mu n nu minus n mu L nu. So let's study what this is, okay? If I want to write this as a matrix, let me start with the components 0, 0. So for mu and nu equals 0, this gives me 1. And here I have 1 over the square root of 2, 1 over the square root of 2. So I have minus 1/2 and minus 1/2. So this gives me 0. Okay, now I have to worry about mixed components, because eta 0, 1 and eta 1, 0 are 0, but n1 and nu and n1 are different from 0. So in this case, I have for eta 0, 1, I have 0 minus L0, which is 1 over square root of 2, and n1, which is 1 over square root of 2, so 1/2. Minus 1 over square root of 2, n0, and L1, but L1 is minus 1 over square root of 2. And this gives me in total plus 1/2, which gives me another 0. This is symmetric by construction, so I already know that this is going to be 0 as well. Now let's study eta 1, 1. Eta 1, 1 is minus 1, so h 1, 1. Eta 1, 1 is minus 1. And I have minus L1 is minus 1 over the square root of 2. N1 is 1 over the square root of 2. Minus exactly the same, okay? So you get this with a factor of 2, because this is 1, 1 again. So this is minus times minus is plus, plus 1/2, plus 1. So in total I get plus 1, and this is 0. And the components 2 and 3 of L and N are 0, so it's just the same components as eta. So this is minus 1 and minus 1 as we expected. Let us now consider a more interesting example, which is that of a sphere in three-dimensional Euclidean space. So this is the standard sphere, and this is your standard Euclidean space, which is R3. So the space is just R3 plus or equipped with the metric G mu nu equal to delta mu nu, where now mu and nu go from 1 to 3. Okay, in other words, if you take coordinates x, y, and z, the metric is dx squared plus dy squared plus dz squared, and this is the metric defined by the three-dimensional Pythagoras theorem, and this is which defines your standard Euclidean geometry. The sphere is defined by this function, a sphere of radius capital R. This is the function x squared plus y squared plus z squared minus r squared equal to 0. Okay, you clearly can define a family of spheres by this kind of generalization where c is a constant, and the radius of these spheres would be, well, to just rewrite this equation in this form, would be r squared plus c, and this is some r prime squared, okay, which is given by this expression. Nothing terribly complicated. Okay, if we follow the prescription that I gave you before, in order to find the induced metric, you should define a coordinate psi equal to f of x, and then you could eliminate one of these coordinates in favor of psi. In this particular case, at least, it is clear that it is more convenient to define a coordinate which is similar to psi. Okay, it would be, if this is psi, we are going to define r as usual by the square root of x squared plus y squared plus z squared. And then the relation between psi and r could be that psi is r squared minus r squared. So you could think that you have done first this change of coordinates to psi and then to r, which is related to psi in this way. But we just go in one shot to r, which is far more convenient. And we not just replace one of the coordinates by r, but we replace the three of them by r and theta and phi, by this standard expression, sine theta, sine phi. Y is r sine theta cos phi, and z is r cos theta. Okay, we know, because we did it in one example in one of the previous lectures, that if we use these coordinates, the metric, the Euclidean metric becomes dr squared plus r squared dz theta squared plus sine squared theta d phi squared. And this combination we denoted by the omega squared. We are going to see what is the origin of this notation and what is the meaning of this omega. Okay, so the idea now is that we can find the metric induced on the sphere of radius capital R by setting the coordinate psi equal to well, to 0, which means small r equal to capital R. So for r equal to capital R, the metric that we get is just r squared the omega squared. For r equal 1, what you get is the metric of, sometimes you write this S2, but let me clarify this notation, okay, which is just the omega squared. So this is the metric of the, this means that the omega squared is the metric of the round 2 sphere of unit radius. Why do we say round? Okay, we can talk about the sphere in a geometrical sense, and then maybe we shouldn't say round, because the sphere is just a set of points which are equidistant to a given point and has a geometrical meaning, and the resulting sphere is clearly round, and for radius 1 this is the metric. But you can also use the word sphere in a topological sense. So a potato, the surface of a potato could be a 2-sphere topologically. Okay, and geometrically you could think of the potato as a sort of deformed or squashed, and well, you can do more things to the sphere. So the word round is there to indicate that if you think of the 2-sphere as some topological space, you're considering a topological space which is really round and corresponds to the standard geometrical sphere, okay, which is the set of points which are equidistant to some one. Okay, so this notation is S2, which is used for the 2-sphere, is sometimes a bit ambiguous, Sometimes it's used in a topological sense, and you have to be a bit careful about it. Now let us compute the vector normal to these hypersurfaces, and let us try to find the induced metric using the standard, the general recipe that I gave you before. So v mu is by definition the partial derivatives of the function f. This function, written in spherical coordinates, has this form. This part is constant, and this gives 2r partial mu of r. And in spherical coordinates, this partial derivative gives you 1 when mu is equal to the coordinate r, and 0 in any other case. So this is 2r delta mu r. Okay, it's clearly a radially directed vector, which is not normalized. To normalize it, we must compute v squared, and we can compute v squared in this way. Okay, and this gives 4r squared delta mu r g mu nu. Sorry. Okay, and this is 4r squared g r. Now you can compute. You need the inverse metric, but the inverse metric is 1 over r squared and 1 over r squared sine squared theta, because this metric is diagonal. It is very simple to compute. So GRR is inverse is 1, and this is 4r squared. Okay, and mu is v mu divided. Here I don't need absolute value because I have taken the Euclidean metric with signature plus plus plus. So this would be v squared and the square root that I missed in the previous part of the video. So this is 2r delta mu r divided by 2r. And this is just delta mu r. Okay, now if you want to compute again n squared, you will see that it gives you just 1. There are no factors anywhere anymore. Now the induced metric is, by definition, this. Okay, because in this case it is space-like, but also the signature is the opposite to the one we are using. This is delta mu nu minus delta mu r delta mu r. Well, sorry, it is delta mu nu if we use Cartesian coordinates, otherwise it's g mu nu, which is not delta. Okay, so let's compute for mu and nu equal r, let's compute HRR. This is GRR, which is just 1, minus clearly 1. This gives 0. And in the rest of the cases, this doesn't count because it is 0 and the metric is just as we expected. And well, you recover exactly the result we wrote above. In the lecture notes, you have you can see the higher dimensional case. So S d minus 1 spheres in Euclidean space, d-dimensional, in d-dimensional Euclidean space. Okay, and the metric is there. Now, before I consider the next example, let me just consider the same situation. Well, rather, the same function f of x that defines spheres of radius r. But suppose that I am working in Minkowski spacetime instead of Euclidean spacetime. What do I get? I mean, are these two spheres? Oh, well, the first thing that you have to realize is that this equation does not describe just two spheres. It describes in Minkowski spacetime the product of the time coordinate, which is a real line, times two spheres. So these hypersurfaces here have x, y, and z are constrained by this, but t is not. Okay, so the hypersurfaces that you get have the coordinate t, and if you go to spherical coordinates, the coordinates z, z and phi. Okay, this would be the induced metric. So maybe we should use some different symbol for it. Okay, dx mu, and this would be just dt squared minus r squared. Well, using the standard notation that we have introduced, d omega squared. This is a Lorentzian metric, and this is because these are, in this context, time-like hypersurfaces. The vector, the normal vector, which has exactly the same form as before, now has absolute value -1. It is space-like, which coincides with the hypersurface being time-like. The last example that I'm going to write is a bit more complicated. So we will be in now direct from the beginning in Minkowski space-time, and the hypersurfaces that we are going to consider are a bit different. Okay, so we are going to consider I say Minkowski space-time. No, hypersurfaces in a space with a signature plus, plus, minus, minus, minus if we are in just 4 dimensions. So this is a 5-dimensional metric, so we consider R5, but this pseudo-Riemannian metric, which is not Lorentzian because the signature is plus, plus, and 3 minuses. Okay, if you want this a bit strange signature, it looks unphysical, but wait and see. Okay, the idea is that the metric here is just ds squared, and there will be dx0 squared minus dxi, where I goes from 1 to 3, and then corresponding to this additional time-like coordinate, I call this time-like coordinate dx minus 1. Okay, I need to call it something. It's not a very nice notation, but it's okay. Okay, this is the metric corresponding to this space. This is R5 with this metric, with this signature. And then I want to consider these hypersurfaces. They are defined by these equations, which generalize the equation of the sphere with some differences, equal to r squared. Okay, so what are the differences? The differences are essentially these 3 minus signs that you have here. In general, this kind of hypersurfaces are called hyperboloids. Okay, but when you have more than 3 dimensions, there are several ways of choosing signs. Here you have 2 pluses and 3 minuses, but there could be 1 plus and 4 minuses, and so on, and you would get different results. Okay, in this case, so this is these hyperboloids are hypersurfaces. So if this is 5-dimensional, this hypersurface is 4-dimensional. What remains to be seen is what kind of hypersurface is this. Is it time-like? Is it space-like? Is it null. Well, since you only eliminate one coordinate, and if you want one eigenvalue of the metric when you find the induced metric in a hypersurface, well, you can never get something which is space-like, because you have two time-like directions, these two pluses here. So you could have something with signature plus plus, minus minus, or plus minus minus minus. This is what is going to happen. So the hypersurface that you are going to get is time-like in a sense, in this sense. In any case, it will be a Lorentzian space. So let's see how this works. I defined r squared as before, and then using this coordinate. Okay. So this is not exactly the canonical way in which I told you how to proceed, because in each particular case there might be a better definition for the coordinates, and you don't have to use this psi that I gave you before, which could be in this case all this formula minus r squared. Okay, so defining this r squared, you find that the hyperboloid equation becomes this one. Okay, and this gives you the idea that okay, you could define a complex coordinate this way, and this complex change of coordinates. Okay, well, this is not, you will see that I am taking you too far, because we have only seen changes from real coordinates to real coordinates, but this is just a simple way of writing a change from real coordinates to real coordinates. You just have to take the real part of this equation and the imaginary part of this equation. These are two real equations that define the change of coordinates between from x minus 1 and x 0 to r and t, and nothing else. Okay, and I am going from two coordinates to just one, because r was given before, so the only thing new is t, because I am using a constraint, so I only have 4 independent coordinates and not 5 as I thought at the beginning. So this is just a smart way of writing the change of coordinates, which simplifies calculations, because now I differentiate. Okay, first I take the derivative with respect to r here, and I get two factors of 2, one from the r squared, another from the square root, so I get r divided by the square root of r squared plus r squared, EIT divided by r, plus this square root, and with the I, r squared plus r squared, and then the derivative with respect to t, which gives me, sorry, this has, there is a differential of r here, and here I get EIT divided by r, I differential t divided by r. Okay, well, if I got this I before, there is only one I. Okay, then this part of the metric, I know how I can replace it by spherical coordinates if I want, because this part of the metric, this definition is just the one we did before. So this can give me the r squared plus r squared the omega squared. The only thing that I need to replace or transform is this part of the metric, which I get by taking the product of this with the complex conjugate. Okay. And this just gives me this. There's an overall phase of EIT over R that completely disappears, I get, so this is, apart from this phase that disappears, this would be real and imaginary, so I just get the square of this, the r squared, and the square of this. Divided by r squared. I just need to put everything together. Let me start with this, the dt part. Then we have the dr squared part. And then the part that comes from the dxi part of the metric, sorry, which was here, okay, and that comes with minus signs, the r squared minus r squared, the omega squared. Let me operate a bit. And then here, r squared minus r squared minus r squared divided by r squared plus r squared, the r squared minus r squared, the omega squared. These two terms drop, and I divide numerator and denominator by capital R squared, and I get this minus dr squared divided by 1 plus r squared divided by r squared, which is the same function that you have here, minus r squared, the omega squared. Okay, this is the metric of a Lorentzian. This is a Lorentzian metric. Okay, and this Lorentzian space-time with this metric is called anti-de space-time. Since you can do this in different dimensions, this is called ADS 4, because it is the 4-dimensional anti-de space-time, and you see that it can be viewed as the metric, the space which has the metric, the induced metric that one gets from this flat metric, which is some okay, all the components are constant when you induce on these hyperboloids. The advantage of constructing this metric in this form, this metric plays a very important role in all the physics that is done now in many developments. The advantage of obtaining the metric in this way is that many of the symmetries of the metric are there by construction, and you already know what they are. Here it is not evident how many symmetries this metric has. Okay, you know what are the symmetries of Minkowski because you have studied them in Cartesian coordinates. If I ask you what are the symmetries of Minkowski in spherical coordinates, you would be a bit confused. You would never recognize translations. For instance, it would be difficult to see. Well, however, if you know that the metric of the Minkowski spacetime has been obtained in a certain way from another space, preserving the symmetries, that you know that these symmetries are there. Okay, here it is the same. You know what the symmetries of this metric are, and if you ask me, well, you may say that you don't know, but clearly this metric is invariant under all translations of all the coordinates. Okay, x whatever plus a constant will leave the metric invariant, plus some generalization of the Lorentz transformations for this particular signature. Okay, it will be some 5 by 5 matrices that preserve this metric, and they are defined like that. You don't need to worry too much about their form. The point is that when you look at this equation, okay, only the transformations that preserve this defining equation, the one that defines these hyperboloids, will be also symmetries of the final metric. because the metric is defined on this hyperboloid. Now all the translations are broken because this you cannot, if you add anything to this x's, this form of the metric changes. But all the generalization of the Lorentz transformations are symmetries of this, just in the same way they were symmetries of the original metric. Okay, this hyperbola is a form which is essentially identical to that of the metric. You could have, if you write this metric in the form ds squared equal to some generalized eta mu nu with 2 pluses and 2 minuses, and you write it like this, then these hyperboloids are nothing but eta mu nu x mu equal to r squared. So whatever preserves this metric eta mu nu, well, with the tilde here, it will preserve it here. So this generalization of this 5-dimensional generalization of the Lorentz group is the symmetry that will be preserved by this anti-de Sitter space-time. It has a name, this group. It's the anti-de Sitter group, not surprisingly. And if you ask about the dimension, it's also 10, just like the Poincaré group. And the fact that the dimensions are the same is no coincidence. But well, I cannot get too much into that. But I hope it is well, it makes you curious, okay, to learn why and what are the consequences of all this. To finish this section and this video, let me just mention that there is one more possibility to get a Lorentzian metric as the induced metric on some sort of hyperboloid from 1 dimension higher. The hyperboloid could be defined by this equation: minus xi equal to minus r squared, but now I takes the values 1 to 4. Okay, so this is 4-dimensional hypersurface embedded in 5 space-time dimensions. And the metric that one considers is the Minkowski metric in 5 dimensions. So this is the x0 squared. The x0 squared minus the xi dxi. Okay, since we mentioned the symmetries and so on, well, while the metric is invariant under some 5-dimensional Lorentz transformations and translations, the hyperboloid is only invariant under the 5-dimensional Lorentz group. Okay, so the metric induced on these hypersurfaces will only be invariant under the 5-dimensional Lorentz group, which, by the way, also has 10 dimensions, 10 independent parameters. Okay, the way to do it, I will just indicate it, and you can fill the details, or the result is given in the notes. You should define again x. Now it's only x1 squared plus x2 squared plus x3 squared equal to the radial coordinate r squared. Then what you find is that if you use this r squared, you get something similar to what happened in the anti-de Sitter case. So x1, x2, and x3 are replaced by r squared, but you can still have x4. So you have this, and this is equal to r squared minus capital R squared. Now, we cannot find a nice complex expression for the change of coordinates, but there is something similar. So we can change x0 plus x4 and x0 minus x4 in this way: r squared minus capital R squared 1/2 e to the plus and minus t divided by r. Okay, so now you differentiate, and the product of dx0 plus dx4 and dx0 minus dx4 is dx0 squared minus dx4 squared, which is what you have here. Okay, once you have used r squared, what you get is dx0 squared minus dx4 squared minus dx1 squared, dx2 squared, dx3 squared, which in spherical coordinates is just minus dr squared minus r squared d omega squared. So you can just find, after differentiating this part, combine everything, and you should get this metric, which is slightly different from the other one. It differs by this sign. But of course this sign is extremely relevant. Okay, it changes completely the physical interpretation of this metric. Okay, and which metric is this? What is the name of this metric? This is the Deceiter metric. That is abbreviated DS in 4 dimensions. While the anti-de metric is very relevant in some theoretical developments that have to do with holography and other formal developments, the Deceiter metric is very relevant in cosmology. Although it looks like nothing depends on time in this metric, this is because metrics in general relativity take very, very different forms when expressed in different coordinates. So you have to go to better coordinates in order to see how this metric really depends on time. Maybe not this time, okay, but some other time. And okay, last thing is about name. So this R that appears here is called radius. Here is the anti-Zeta radius. Here would be the Zeta radius, and it is related to the cosmological constant, which I haven't introduced for you, but I am telling you now so you remember when we mentioned the cosmological constant.